Thank you. This is actually quite an honor. I'm Julia Lonkin of the Foscar project. I have been basically 3D casting aluminum here for the last 6 months or so. And it's been an interesting process. I actually have a background as a software engineer, not really anything resembling hardware normally. I've been developing all kinds of things around the Linux kernel and some PHP work, but I recently got a bad case of carpal tunnel, so I kind of had to ditch the software career for something a little less repetitive stress. I've been building 3D printers over the last 3 years, so I decided that it would be a good idea to kind of push that technology a bit forward. I've been looking at the situation we have with proprietary hardware in the automotive industry for a while, and decided basically that it was time for us to have something a little more solid as far as an option for repairing our own vehicles. Where I come from, not having a vehicle means not having a job, not being able to get to medical events, basically not being able to have a lifestyle. When I started on the aluminum printing sort of quest here, it was, of course, to print up some durable components for the vehicles that I'm trying to produce. I've been basically working on the entire chain from the design tool of implicit CAD all the way down to actually casting the aluminum itself. For the automobile's computing system itself, we've been looking at using as many free and open tools as well to make sure that we can actually trust the machinery that we're driving around. Now, currently, the state of the art for if you want to take a piece of plastic and convert it into a piece of aluminum it's the lost PLA technique, which is to say that you lose PLA plastic whenever you're producing the part. You put the part inside of a mold that is made out of sand and made out of plaster of Paris. Then you let the mold set up after attaching kind of an inlet and outlet for the aluminum in the mold. And then you put it into a propane-fired forge. You wait for roughly about 5 hours for the plastic to actually burn and for all of your inlets and outlets to burn out. And then you wait for it to cool. You take this and put it into basically a box full of sand with a little bit of extensions on it to let the aluminum flow into it, and then you pour in liquid aluminum. It's a time-consuming process that requires people who have a lot of experience at dealing with, basically blacksmith-type tools. It's roughly 24 hours to get a part out of it. So what I've been looking at is, of course, with a 24-hour delay, it's hard to have any sort of turnaround, and the results are not necessarily guaranteed. I mean, I've been having roughly basically 1 in 3 success rate out of my process here, and that has to do more with the pieces that are in common with lost PLAs than anything I've been managing. You have to sit there and burn propane for most of the day, which is a whole lot of energy. And we have, in practicing this sort of a technique, we've actually run into several accidental fires. So sort of not to burn oneself down is important. When I was looking around at ways to actually impart energy into the vessel, I was thinking, microwaves are very good at getting into a surface and getting to a target. So I started this process, looking at 3D printers and thinking, well, why don't I just make an aluminum extruder to actually extrude aluminum? Well, after about 1.5 years of working on it, it turned out that the method I was going down required me to use diamond-like carbon deposition technologies, which I don't even have. So I ended up scratching that after quite a while of work. So I looked at the lost PLA techniques, and decided these are, reasonable techniques, but all of this propane is probably a bad idea to be doing in any sort of a residential zone. So at that point, I started looking around on YouTube and all your various, video sites, and saw at least roughly 15 people who claimed to have microwaved aluminum to the point at which it was actually liquid. Now, some of those I found used like Woods metal or used other lower temperature metals and then said, hey, you can do, metal in the microwave, but, aluminum's hard. Now, I went ahead and built a forge kind of inspired off of the designs that they were using to melt down my aluminum, but then I figured, well, I can melt aluminum in the microwave, but what do I do about this mold technique? Because, I still have to have an empty mold to pour the aluminum into in order to produce parts. So we went ahead and created a mold process, but we were still having some real trouble with the microwave forge. I've only gotten it to work a limited number of times and have blown smoking holes in at least one microwave. And so we went ahead and set up this small propane-fired forge that I found directions for on Instructables, which is basically the size of a large coffee can, a lot easier to have lying around and a lot more space sensitive. So we started working with that one so that we could get liquid aluminum for our molding process and start actually developing our molding process. This is what the microwave forge that I created the first time looks like. This one here actually worked. So it's basically a mixture of fire cement and perlite. So not silicon carbide, but another silicon substance, and basically a gardening supply, perlite. In order to produce it, it's a large, complicated process, so my apologies if I skip through some of this. This is still something that is a little bit on the beta level because we've only managed to get this to work a couple of times, and I've produced almost as many forges trying to make designs work as I have gotten cups full of aluminum. So basically, the entire concept is you make yourself a vessel for holding a lot of heat, and then you put on the inside of this vessel some silicon carbide grinding powder that you see over there in the consumables. That is a microwave susceptor, which is to say that it's a material that when it receives microwaves, it actually heats up rapidly and will just conduct this heat outward without going into a liquid or a gaseous stage. So it just gets warm and you can just dump lots and lots of microwaves at it. So like I said, we're using fire cement and perlite for the vessel itself, which we end up having to make in multiple kind of waves. We make the inside of the chamber first, then we make the outside of the chamber, then a seal on the top of it, and then a lid to go down onto the seal. We have to use an oven to actually cook all of this fire cement until such a point as it's actually solid, because it comes just as a sort of a putty. And we mix that with the perlite and kind of construct our vessel from there. The inside layer we end up putting together by using sort of making our own cardboard box and then sort of smearing the stuff around the cardboard box. The box has to be roughly the size of the vessel, which in this case is a steel cup, that we're going to melt the aluminum in. So we don't allow the aluminum to touch the actual silicon carbide or the box itself. That way we have something to pick it up out of the box with. The outside layers, we basically just make the thing as thick as possible that will still fit in a microwave. We do have to make sure that the microwave itself has the little turning table in the bottom of the microwave. We take that out so that the kiln is not sitting there spinning, and we can actually make it rectangular instead of, round. The seal and the lid were actually a pretty complicated process because you want to get a very tight seal on the top of this thing. So we made as flat of a seal as possible by hand. And then once we had that done, we kind of just took and made as close as we could to a flat lid, let it heat up for a little while in the oven, and then put the entire chamber on top of it as sort of both a weight and a guide to make it form into exactly the same shape. Once we have the chamber itself made and we have a lid, we basically just take the microwave susceptor and we mix it with sugar and water and just basically paint it on the inside of the vessel. So the sugar serves a function of holding all of the silicon carbide in place, because when you burn sugar, you get pure carbon, which sets up very nicely with the silicon carbide. So it kind of just makes all the silicon carbide stay on the walls exactly where you paint it. I used a oven to apply the first layer, and after you've got the first layer of your silicon carbide applied, then you can actually just use the microwave for applying the rest of the layers, because of course the silicon carbide is just going to get hot. So that was very convenient, because you're first baking something in the oven for an hour, and then you put it in the microwave, and it takes 5 minutes. This here is one of our proof of concept melts. This is the first time I successfully got aluminum to melt in my microwave. It took me basically 2 hours and 40 minutes. Set it high. And when I went to take it out of the microwave, I had to, of course, use fire gloves and keep this microwave outside, insert the standard, never use a microwave that you're going to use for any other purpose, and don't do this kind of stuff indoors. Liquid aluminum is not good for your floors. So once the aluminum actually liquefied, I didn't have myself a mold prepared at the time. I honestly didn't expect it to work after the third kiln that I had built. And it's like, okay, I have a cup full of liquid aluminum. What do I do with it? Nothing. Okay, so I just let it cool in the cup. Now, aluminum, when it's cooling, actually contracts by about 3%. So as a result, it just kind of pulled right out of the cup, because it didn't bind to the edges. The cup is made of steel. The aluminum is obviously made of aluminum and aluminum oxide. So no, it did not bind at all. I just pulled it kind of right out of the cup. That is actually a steel cup that I picked up for $1 at a thrift store. That's your high-tech crucible here. Now, when we went to make our small propane forge, basically based on the Instructable link, we set up and we built a bigger one, honestly, because we wanted this process to really kick out aluminum as fast as possible. So we didn't increase the size of the crucible, the vessel that we actually hold the aluminum in. Instead, we went outward on the size of the forge itself. So that is a standard milk crate you see there, and that is the size of the forges that we're making. So we basically just build one that's, roughly 13 inches on each side. Once we've got the forge up and running, this is what it actually looks like after running for quite a long time and putting out a whole lot of aluminum. This one here has, as you can see, there are cracks in the top of it. These do break down over time, but we've gotten roughly 40 or 50 melts out of each one of them that we're producing. So as you can see, we've got a chamber there full of aluminum. There's a set of basically steel tongs that we put around the crucible that we hold the aluminum in. So they're always part of one unit, so you can pick it up, of course, again, with fire gloves, not your bare hands. So you can pick up the crucible out of the chamber and pour your aluminum. We use the chambers themselves are made out of, or the crucibles themselves are made out of old propane bottles, the small ones. Make sure that they're empty before you go cutting them in half. The advantage of using that, other than the fact that it's a standard size, is it's also solid steel, and that steel binds to the aluminum oxide whenever you're melting down aluminum. What we're actually doing for our aluminum source is we're actually using old bicycle rims because we can get them for free. So free aluminum, hard to argue with. And it comes with some impurities on the outside of it because it's, obviously been through its entire life cycle and then been warped and then been what have you. So the aluminum oxide that coats all the aluminum that you see has to go somewhere. So it sticks to the sides of this chamber because the chamber is made of steel, and apparently it sticks to the carbon in the steel. So that way you get a nice clean pour of pure aluminum out of this method. We're also using a stirring rod for it that's made of steel so that any aluminum oxide that it happens to come into contact with also binds to the stirring rod. We've got a burner there. We've used basically burners that we've picked up at our local hardware store, and those have worked out fine, but over time they kind of get expensive to go through because one of them lasts like 20, 25 burns, and then something goes wrong with the end and you've got to go get another one, and they're not exactly cheap, like 40 bucks or so. So we went and found another Instructable for a home-built burner that is what you see in the picture here. It's actually much solider construction, so we haven't had any problems with it whatsoever. We're using basically the giant-sized propane tanks, so you can see our line to the propane tank there, and we're using a regulator directly attached to the propane tank to control the heat level at our burner. Now, for the microwave molds themselves, this is actually the exciting part of it to me. The microwave molds itself, you have to make up this investment, which is basically just a goop of water and perlite and plaster of Paris. You then take your 3D printed object, you attach a series of sprues and inlets, and you attach basically where your aluminum goes in and where your aluminum goes out, and then you put it into a piece of Tupperware that is very, very cheap and flexible because you want to be able to just pop this out. Don't use the solid stuff, use in my case, the dollar store stuff. It works out very well. And you can just kind of pop the whole combination of your 3D printed object and your investment material right out of the Tupperware. Works great. This here is one of the 3D printed objects being set up. This is actually one that I've got here on the table as well, so you can see the result. The styrofoam there is for your inlet and outlet channels. So the styrofoam on the right-hand side is where we're going to be pouring in aluminum, and the styrofoam on the left-hand side is kind of where air goes out. As you can see, we attach where we're pouring in a little bit more to the object than the outside because we want a little bit of pressure at the object to make sure that the aluminum adheres to every contour of the negative. So you end up with literally every ridge of your original 3D printed object visible in the aluminum result. Like I said earlier, we're using a susceptor, and we also use the susceptor in the microwaving process for our 3D printed parts. So the 3D printed parts, we basically take what you saw on the last slide, and we just kind of make this spray here out of, again, susceptor powder, sugar, water, and a little bit of alcohol to get it to bead up. And we kind of just spray the surface 5 or 6 times, letting it dry in between, so that we get a microwave susceptor right there at the 3D printed object. What this does is it allows us to basically use the mold. Since the mold is transparent to microwaves, the energy from the microwave actually goes directly to the 3D printed object and all of its guides and sprues, and skips up the whole process of having to heat up this item that is made necessarily out of highly heat-resistant substances. So as a result, it cuts down the time considerably. we're looking at roughly 2 hours between the time in which we have a 3D printed part in our hand and the time at which we've got a mold in the microwave versus, the 8-hour approach of the standard loss PLA. So there's 6 hours of your life back and probably a little bit cheaper life insurance because you don't have to use propane for this step. This is one of the molds. Actually, this might even be that mold. I don't quite remember which one it is. In the microwave, actually being microwaved out. So we wait just long enough for the mold material to harden. Then we pop it out of the Tupperware container that we used and put it in the microwave and basically microwave it until we can get all the water to leave the mold. Normally with lost PLA, you basically got to leave this thing sitting around long enough for it to get solid, which sometimes can be days depending on the size of your mold. In our case, we just completely cheat. We throw it in the microwave, we nuke it until the water is gone. Now, as it's doing this, we have to microwave it on low because you don't want to basically cause air bubbles that are inside of it to expand from steam. And we actually had a lot of molds for a while that were exploding on us because we didn't know what was going on with it. The air bubbles were collecting all the steam, too much pressure on the inside of it, and you're just kind of sitting there and you hear a boom out of the microwave and all you've got is a mess. So what also happens is that the water that is exiting the object will try to bead up on the surface. So basically your microwave tries to flood. You have to get in there with a towel and about every 15 minutes, towel it out and remove all the water that you can find. We did kill at least one microwave by flooding. Once you have your mold once your plastic has actually burned out of the mold, then you're ready to pour in your aluminum. Now, in order to get your plastic to burn out, of course, it takes a little while to burn the plastic as well. You're looking at about an hour on simple objects to burn the plastic. And the real way you can tell that you're done burning plastic, of course, because you can't look inside of the mold, is you kind of microwave it until such a point as you can see smoke leaving the microwave, but you try not to microwave it much more than that because you want to make sure that you don't overheat the mold itself. If you put too much energy into it, the mold itself will try to burn, and at the point at which your mold burns, you're pretty much done. So you kind of microwave it just at the right point. This, of course, varies per machine. I have found no universal methods when it comes to what settings should be for what microwaves. So it's very trial and error. Expect your first couple of parts just to die. Now, once you have a mold in your hands, you've got to put these sprue extenders, which are those two Red Bull cans that you see there. Those are for the inlets and the outlets for the aluminum. So we basically bury that in a box of sand and get the sand all the way up to the top of it. That way, whenever we pour in our aluminum, the sand kind of just holds everything in place because those Red Bull cans do not put up to liquid aluminum very long. So this is us actually using our little forge to pour aluminum into the mold that you just saw. So this is what it looks like in production. You've got a vessel full of aluminum that you have superheated, which is to say that you've brought to at least 800 degrees Celsius with standard propane, and then you kind of just pour it into your microwaved mold. This is what I consider our temporary hybrid approach, because the little forge will get the job done as far as melting aluminum, but it's nowhere near big enough for you to put any 3D printed objects and molds and do any of the cooking that you normally would for standard loss PLA. So this gives you, roughly just enough hardware in a small space that you can get this process done. As you can see, there's usually a little bit of plastic residue still left on the inside, but you want to make sure there's as little as possible still in your mold. And it does catch fire, and in addition, so does the paint on the Red Bull cans, so does the duct tape, so does the, but none of this matters because at that point you've got your aluminum in the right place. And once you're done, you end up with this, mold that has been, well, it's had aluminum poured in it. You've got to kind of just break it apart, and then you get, it's kind of like unwrapping Christmas presents. You get whatever you've got on the inside, and you're like, ooh, is this really, oh, really? It's kind of nice. As I was saying earlier, the combination of using a small propane-fired forge and using a microwave for your molding techniques means that you get to rapidly do this process. I have, in periods of about 4 to 5 hours, gone from 3D printed thing to waiting for my aluminum to cool, versus, the standard process, which sometimes can take days, depending on how thick your mold is. And so this here is actually one of our first good successes. It's my 3D printer printing more 3D printers, which seems to be all I do with my 3D printer. While I have been building them for 3 years, I don't know what it is, but all I see is more printer parts every time I try printing something. So I reprinted my machine over again. Of course, most people with a Prusa-style machine are going to reprint their machine to get better parts. Well, I reprinted my machine partially to get aluminum parts. So it made a very good practical application. Now, when you're printing a plastic part, you can, of course, get away with having basically almost no infill because, well, you don't have to worry about how solid the part is. You just have to make sure that it will hold liquid from being inside of it. That's a pretty low bar. You also print the parts at 103% because, as I was saying earlier, aluminum contracts just a little bit. So you basically just hit your stretch in whatever particular program you're using to print and stretch it up to 103%, then hit print. That's really all you have to know about printing the plastic ahead of time. It actually means that your plastic parts will print pretty quickly too, because I know I have spent 4 hours trying to print a solid extruder before, and when I can spend an hour and a half printing a solid extruder and then turn it into a piece of aluminum in 4 hours, that to me is a much nicer scenario. This is me attempting to print extruders out of my machine. That's still a little bit too large for our process right now. As you can see, the one on the right has most of its components intact, but you see the inlets and the outlets for the aluminum there. I put them way too thick and way too attached. And one thing to note about this aluminum that comes out is it's actually, in my experience, harder and solider than most aluminum that you deal with. And so as a result, it's very difficult to pull away from the extrusion, to pull away from the object itself. The one on the left, I actually left a little bit of space so that I could try to cut it off. This is a suspension component for kind of this little RC car type thing that we were trying to produce. It did not turn out well because we casted it, and instead of using sand, we used vermiculite, which was a really, really bad idea. Don't do that, it's too light. As I said, we've been working with implicit CAD, which is a CAD application for designing our parts. We like parametric parts. So when designing, when trying to design a series of car parts, we want to make sure everything lines up. So we're using a functional-based language to actually design components. We've had some people trying to get us to 3D print their objects, of course, using various non-free softwares like AutoCAD, for instance. It just doesn't have what we need in it. Implicit CAD is it's our language of choice, and we kind of just use it to compile a design from a solid piece, from just this plain text file all the way into an STL file for printing. This is kind of what some of the examples in the language look like. So in order to implement like a test suite in it, we basically took and Well, we basically designed the same component as many different ways as we could in the language so that we could compare the MD5 sums to the STLs. Designing things like a gear in it was reasonably difficult. I had to learn trigonometry to do this, which was not easy for me at all, because I'm actually natively a C programmer. So all of this 3D design, all of this aluminum pouring, it was not necessarily my forte, but I had to get away from a keyboard. The language allows for some severely rounded objects. That's why we've labeled these all unicorns, because I don't even know how to do this in many other languages. But it's like the object on the right, it's kind of twisted as it goes upward, which is a function on an extrude of a, I can almost not even explain it myself, but it works out very well. We ended up having a whole lot of issues with the software because it had been abandoned for about a year. And anytime something's abandoned like that, you end up with bit rot. So we ended up throwing a test suite on it and basically taking over the project with the original maintainers, blessing. This is, I still don't quite know what this is, to be honest. It was trying to be a gear, just like the gears earlier, but I passed in the wrong value to the wrong function, and I don't think that's 5 teeth anymore. As I was saying, the software ends up with some interesting bugs. So this is attempting to be one of those disks that I was showing earlier, but the multi-dimensional scale function was just kind of broken, so it's an oval. It makes sense when you know the code, but when we're comparing the files, it sticks out like a sore thumb. So we get to run tests of each individual section of the language. The fuzz in the middle of that, I still don't quite know what's causing that. That again is another attempt to be a disk with a hole in the middle. No. So this here is an attempt to be a gear. It has 5 teeth. The 5 teeth are technically around it, but that's about all you can say for this one. The 5 teeth are, if you actually break out the measuring stick, they're not even actually evenly spaced. In addition to the one being, and that is not spaced for a 6th one on the other side. If you measure it, it's not there. It's like, it would need 6.5 teeth for this. This was a regression in the language, which is to say that at some point in the language, this exact code worked. I can give you a Git revision. I swear, it did work, but then somebody changed something, and this is currently the result. We've been working with implicit CAD here for about 3 months now, so I've been sort of just tearing apart the language, which works out pretty well for me. I mean, it's all functional, all just straight math, and it's based on Haskell, which I'm starting to enjoy, even though I really don't understand at least half of it. But the nice part for me is, as a software developer, I kind of got my start pretty early working on ray tracers, which it's some complicated math, but it's something that I got very comfortable with at an early age. And this engine kind of uses a ray tracer on the inside of it in order to decide where the triangles go. This is one of the more complicated things I've been producing. I think I may have some of the most complicated implicit CAD files ever at this point. Some 900 lines of just object description. So this here is basically a ring around a track mold. We're making these very flexible tracks for a series of basically RC cars. So they have kind of little bitty tank treads that are, that can climb, for instance, the steps up to the stairs. So this is kind of the outside of that track system. This is an attempt to be the track itself. As you can probably see, there's still a little bit of gaps in some of those teeth, which I still don't quite understand. There's a couple of bugs still in the implicit CAD system that I'm ferreting out. The same thing is kind of holding here. As you can tell, this is kind of trying to be the inside of that mold, but you see all the little threads that are sort of standing up there? I don't quite know what's going on with that either. A union, of a circle, of a something of that sort. Now, the reason that we actually did this all was to try to have aluminum parts for our automotive process. So that was actually why I started down the path of aluminum printing, even before my hands started to give me any sort of difficulties. I was trying to build a aluminum extruder for quite a long time and just kind of had to throw my hands up at it. We're looking at this as basically two layers, which is to say that the first thing that we're trying to produce is, we're calling it Allen, which is a attempt to put parts on people's currently existing vehicles, let them maintain it longer, let them add whatever sort of flares they want to the vehicle. For instance, one thing that I walked outside and immediately noticed about my cars was no folding mirrors. Folding mirrors are kind of nice, but it just was not an option in that year model, and there's just nothing I could do about it other than, I'll try to 3D print the whole process. When we're trying to build up replacement parts for these cars, we've of course got to completely reconsider how security is working. So in our current automobiles, well, the newer ones are a security nightmare, and the older ones just don't have all the features that we're used to liking. So it's like, how many of these talks have you been to, or how many of these have you seen where somebody is owning the car of the week and showing you how you can slam on the brakes, or how you can hold down the accelerator, or lock everyone in the vehicle? The computing security in a car is a nightmare because from my perspective, we tend to treat car computing more like a wireless router than we do a hospital. But wireless routers, when they crash, no one dies. Cars, when they crash, well, the hospital is involved one way or another. We've been trying to design the internal network of it sort of in a segmented off system, so that if somebody ends up owning your CD player isn't able to tell your brakes, hey, slam on now. Having this sort of separation makes some good sense. We're of course doing this from we're looking at this sort of as the blue team approach versus your red team approach for your current cars. Most people who are working in car security right now are working in the ability to break into them, not necessarily in the ability to actually build them up from the ground. So we're trying to build them up sort of in a from scratch situation. We're licensing everything as freely as possible, and as freely as we can even consider. So we've done a lot of research into hardware licensing and had to figure I think that the TAPR OHL is currently as open as it gets at the moment, but it's kind of an attempt to be the GPL in the hardware world. And of course, we're using GPL version 3 for all of our software designs and all the software that we're using. We've got a canary on our site, so if we end up with any sort of we can't talk about whatever letter we just received type of scenario, you can at least tell that we're not talking about it and not updating our canary date. And so you can tell if we've received our, you must implant this chip to all cars notice. We are working, of course, out of the United States, so minor concern. And as I was saying earlier, we're trying to segment off the networks. This includes having, deciding what direction data must communicate and data must not communicate. So we're basically trying to limit it as much as possible inside, as much communication inside of the vehicle as possible. Now, at the end of this, we end up with basically your garage being what I think my father would have referred to as, a garage back in the 60s, where people actually tooled with their cars, improved their cars, played with it and manufactured small components of it on their own. Nowadays, There's no such creature. Do you have a plastic molder in your garage? I mean, none of this is acceptable. But back whenever cars were made of steel or made of, more durable materials, that was a possibility. Now, of course, there are a couple of problems with trying to manufacture these things, which is we've got a lot of federal standards involved, which seems to be our biggest issue. And there's a whole lot of communication occurring in modern cars that we're trying to eliminate. So we're trying to make this something where you can do all of this work yourself. Well, that didn't format right. This is what you get for compiling your presentation on the stage. As you can tell, we're looking for as much help as we can. So if you would, give me an email, contact me on Diaspora, and when you're emailing, try to unline wrap that PGP fingerprint. Thank you kindly.
We will have a Q&A session now. We will have a small Q&A session. Please line up on the microphones throughout the audience, and we will call you out. Please ask questions. Okay, microphone 3.
Hi. Hello. Hi. The intersecting face problem that you were showing in some of your renderings, I think that's actually that's a result of the math library. It's a lack of precision. You're getting very close to the surface. I've seen this in other 3D modeling where if you get like just exploding geometry, nans all over the place, and if you shift the camera by even like 1/10 of a degree, suddenly things start to resolve. And it's because your precision is not high enough. In OpenSCAD, where I've run into this problem before, I get around it by just adding like another 1/10 of a millimeter to my model, and it pokes through successfully, and you get the actual hole that you're looking for.
Yeah, that's absolutely correct, and kind of since I'm maintaining implicit CAD, I have sort of not fixed my model in that fashion intentionally to remind me that this sort of a bug exists so that I can get the math to come out exactly right. The little threads and needles there, as I 3D print that object, of course, those are just going to fall off anyway. So,
I did have a quick question. I might have missed the slide. It looks, implicit CAD looks a lot like OpenSCAD.
It does.
Is it a fork, or is it inspired, or is it just Haskell versus whatever the contrived language they're using?
It is kind of inspired by, which is to say that implicit CAD uses what's called ESCAD as its language, so it should be SCAD, but it's being interpreted functionally and the semantics are a little bit different, so it is a derivative of the language, but the code bases are completely different.
Okay, so this is a new original thing that I should go check out then. Thank you.
We have another question at microphone 4.
Hello.
You mentioned silicon carbide a lot. Would it be suitable to use only carbon for the same purpose?
Actually, not at all. What's going on there is in a microwave, whenever you're actually microwaving any material, the microwave energy is being absorbed because it's an electromagnetic vibration, and you need a molecule in there that is not symmetrical. And the silicon carbide is kind of just a little bit off. If you've got pure carbon, then even carbon chains, they don't vibrate, so they don't heat up at all.
Microphone 3.
Okay. You had a problem with trapped air bubbles in your plaster of Paris with the exploding molds. Did you try investigating the mixing methods for plaster of Paris used for making porcelain molds? Because you can mix your plaster very well with nearly no air bubbles in the first place.
Part of the problem there is the perlite substance itself basically is almost an air bubble that is trapped inside of a mineral. So perlite is this very spongy mineral that we're just kind of all throwing in our gardens, and there's not that much of it, unfortunately. But as a result, there are always air bubbles because we use the perlite to sort of space it out, because the plaster of Paris not only will it absorb microwaves just slightly, but in addition, plaster of Paris is not enough to stand up to liquid aluminum. The plaster of Paris gets burned just a hair every time. So there's actually just a little bit of burned plaster of Paris on the inside of the mold. The perlite kind of, spaces things out so that you have that insulative effect.
And one question, did you try having cold cast aluminum parts in your furnace?
I have not.
Okay.
Not even familiar with the process, actually.
Microphone 4.
Thank you for the great talk. You're really brave. My interest is in psychonautics, which is hacking of the human consciousness. In your first slide, you talked about biohacking being your long-term goal. Can you expand on that?
Well, actually, part of the reason that I've been trying to build 3D printers in the first place, I'm previously from the medical records industry, so I've always been trying to kind of advance our medical industry in one fashion or another. But in this case, I've been looking at my 3D printer and going, how do I use that? Well, the precision is not there in a plastic 3D printer. Everything is wiggling around no matter how you handle it. You're looking at 100 microns of precision, which is just horrible whenever you're trying to produce any sort of biological material. So I looked at that and went, how do I improve the quality of the printer? And so I decided solid aluminum parts would probably increase that quality to such a point that we can print at a fine enough detail to start actually attacking real, bioprinting problems.
And do you have a plan on when you start to work on this?
After my first car is off the line.
Best of luck. Thank you so much.
Thank you.
Microphone 3.
Thank you very much for the very cool talk. I just wanted to ask a question. Have you kind of considered the other way, i.e. removal methods, such as, as like CNC or something?
Lots of material.
I mean, what's the advantage, disadvantage of kind of...
The advantage is, well, getting a hold of large chunks of aluminum is expensive. I mean, and this way I'm literally recycling old bicycle rims that I'm getting for free here. So it's a lot cheaper that way.
Right. Okay, but it would still work, like if you...
Sort of. Whenever you're doing that kind of work, you end up having to have 3 or 4 or 5 axis machines to get the sort of, angle on the inside of the angles upward and the hole on the middle of the, and 3D printing really just gets around all that problem for you already.
All right, thanks.
Microphone 4.
Hi, yeah, thanks and everything. I just have one question with respect to your furnaces. I actually have absolutely no idea, but a friend of mine used induction heating to melt aluminum, whatever. And have you looked into that? Because that looked really impressive what that guy did, and he was like 15 at that time. He probably shouldn't have done that in his own house, but
again, no liquid aluminum indoors. There's a rule for that in my house. I've only broken it once.
So he seemed to be able to melt the amounts of aluminum that you are showing, like in a matter of 3 minutes or so.
Induction heating does work, but at least the one unit that I have seen that has been documented for this purpose, it takes 240 volts, which is not even available in the house that I'm in. So just to start with, it's consuming a lot of energy. Now, a microwave consumes a lot of energy too, 1,500 watts times, 2 hours. But at the rate at which I'm getting that, it's roughly 25 cents an hour. So, pretty cheap.
We may have 2 questions left. So, microphone 2.
Hi, thanks for the inspiring talk. Have you calculated your energy? Have you calculated your energy costs? Because it's nice to do such stuff, do it yourself, but I think aluminium industry and heavy metal industry is one of the most power-consuming industries in the world. So how can we scale the energy consumption down? Actually,
that was part of the win from my perspective, because by taking 8 hours of propane and converting it into 2 hours of electricity, well, one, it's a lot easier to produce. Well, it's a lot easier to produce electricity via actually useful, actually carbon neutral means. And in another for another part of it, basically, I'm getting my energy at 25 cents for 25 cents per microwave per hour, which is, well, probably the first time that unit has ever been used. And as a result of that, being able to microwave down these rims, being able to melt down currently existing aluminum into new shapes gives us a lot lower power consumption than the manufacture of this stuff. And in my case, I'm literally keeping aluminum from going straight into the landfill. So even my failures of parts turn out to be, I can throw them back in. I don't have to consume all the energy it takes to actually separate aluminum from bauxite. That's actually your real high energy consumption. So 95% of the energy that is being wasted was wasted in the production. Changing it from one aluminum shape to another aluminum shape is actually a really low energy cost comparatively.
Okay, microphone 3.
Hey, you mentioned using the steel tanks, but do you actually need any sort of additional flux or anything to work with aluminum like this?
Actually, not at all. It worked out quite excellently. The steel holds onto the aluminum, basically to the aluminum oxide, just kind of bonds right there at the edges. So after those steel tanks only last about 3 or 4 prints, and by the time you're done, you've got about 2 or 3 centimeters worth of aluminum oxide just all over the edges of the tank, and it doesn't have as much volume to begin with anyway. So no fluxes involved. The most complicated part of that is when you're trying to heat up your first little speck of aluminum, make it a little speck of aluminum, because of course aluminum conducts heat very well, even in its liquid state. So if you're trying to heat up a large block of aluminum in your forge, you've really got to throw in an itty bitty piece to get liquid first, and then start feeding in bigger and bigger pieces. We actually start with a piece of our Red Bull cans as part of the starter.
Okay, we just try to make the camera work here, and you may show us some of your work here. Last chance.
Please, oh please.
Something happened there?
Actually, I have one photo that was in the slides, but that doesn't show you the...
Okay.
Yeah. Okay, let's take the big cam. Just a challenge for the cameraman.
This piece here, if we can actually get it, is it visible yet, or?
No zoom? Okay.
Okay, there we go. This is, like I said, one of the, as you can tell, I'm kind of a little bit addicted to Red Bull sugar-free whenever we're doing this. So yeah, lots of runs down to the local market to pick up Red Bull cans for our sprue inlets. So those are kind of our extenders, and this is what it looks like when you get one directly out of the process. So it's like the only thing here. The other component that was interesting from my perspective is this one here is the raw chunk of aluminum that we got out of our process itself. This is from the microwave forge. So I've honestly only seen about 7 or 8 examples online of people actually getting a microwave to work for this. So I'm pretty proud of this one little chunk because it took a lot of work. This used to be some Pentium 4 heat sinks. Apparently it's not just the Pentium 4s that melt. This here is, of course, the section of a process-style printer. This is called the Elks Vertex with Foot, if I remember correctly. It's out on Thingiverse. So You can see just some minor defects in it. If I get the angle just right, you can see that little crack there. That's a little air bubble that was in the mold. Well, that's a section of plastic or an air bubble that was in the aluminum when the aluminum went through. But the part itself is not only serviceable, I have printed with it on the machine. So functionality wins the day there.
So we are right on time. Thanks to Laura Longton, Julia Longton, sorry, for the nice talk. Please take your trash out. And the next talk will be reproducible builds.
Thank you kindly.